leader for this conference. So I think we have 5 interesting talks in this session. 4 with the regular time, which 17 minutes presentation time, and the final talk we have a shorter presentation time of only 8 minutes. So to lose no more time, I think we can start immediately with the third presentation, and the presenter is Sainyam Galhotra. Please.
Thank you. Thanks everyone for coming. So I'm going to present this joint work with Donatella, Barna and Divesh. I'll start with the motivation of the problem of entity resolution and later move on to the contributions of our work in this domain. So as you know that a lot of data on the web is present in the form of images, text, structured records, descriptions and so on. And we need to figure out that what are the entities present in these records on the web. So all this data can be modeled as a noisy union of cliques where each clique refers to an entity. And we would like to infer those. For example, these are the collection of images of people, different people, and we want to figure out that who are those people in these images. And every pair of node in this graph is connected by a weighted edge where the weight of an edge refers to the probability that the two endpoints refer to the same entity. For example, in this graph, the green edges mean that the two endpoints of the edge refer to the same entity, and the red edge means that the probability is higher for them to be different entities, and thicker the edges, the higher the probability values. These probability values can be generated using Jaccard similarities or other similarity measures too. So given this input, we would like to figure out what are the entities present in this data set and output those clusters. And each cluster corresponds to a single entity. So given this problem, let's see what are the easy solutions we could come up with, easy automatic solutions which we could come up with. So one of the common solutions could be that we could figure out the connected components over the green edges. Green edges are the ones which are highly likely that they are the same entities. So we could calculate the connected components of the graph and return those as the different entities. But as you can see that connected components so this result is not correct. And as you can see that connected components won't give a good answer if there is a single green edge connecting two different clusters. So this algorithm won't work well in practice. The other solution you could come up with is that I could run correlation clustering over the graph and return those clusters. On this example, this also does not give a good result. And as you can figure out that if the edge weights are not very high, they are higher to be on the green side, but they are not super high, then some nodes like these get removed out of the cluster. So let's look at the ground truth and see how we can model this problem. So this is the ground truth of the images I showed to you. And we model this problem through an oracle. Oracle can be considered as an abstraction of the crowd, where we ask the oracle whether these two images, we'll ask an edge to the oracle that whether these two images refer to the same entity or not. And the oracle will return an answer yes or no. Based on those answers, we can figure out what the actual clusters are. So what would be the naive approach of asking the oracle? We could ask the oracle random node pair queries, and oracle would return yes and no. And if it says yes, we'll add them to the same cluster, and if it says no, we'll continue. This is a very dumb approach because it is order n squared. It will take order n choose 2 time to complete the entity resolution procedure. The smarter approach could be to look at the edge probabilities of these pairs and sort the edges or follow a procedure using those probabilities as a guidance to ask queries to the crowd or the oracle. So let's formally define the problem statement first. So we are given an input as which has been modeled as a noisy graph, and we want to output the set of clusters which refer to the entities. And the problem which has been, and this problem has been studied a lot in the literature, which says that given an oracle which can correctly answer node pair queries, whether they are a match or not, we want to devise an optimal strategy so as to ask the oracle queries, and we want to maximize the progressive recall with the sequence of oracle queries. The progressive recall is defined as the area under the recall query sequence curve. But as you can see here, the oracle is assumed to give a correct answer all the time. But as I mentioned, now that Oracle could be considered as an abstraction of the crowd, and the human users can always make mistakes. Even if you calculate the majority vote over the answers given by different human beings, they can still make mistakes. The answers can be difficult. Like if I show you two images of two twins from different angles, there's a good chance that you will make a mistake on those images. So this assumption is not a very realistic assumption which has been made in the literature, and we get rid of this assumption and we consider a noisy oracle which can make errors as we ask questions to the oracle. So let's look at one of the prior works which were proposed in 2013, which says the edge ordering strategy. This algorithm says that we'll order the edges to be queried in decreasing order of the edge probabilities, and we'll join the nodes as the clusters grow. Like the first edge it queries is the thickest green edge, and we get so the tick on the edges shows the answers which the crowd gives us to, the oracle gives us to. And as we grow the clusters, it can grow different subclusters also, because we're growing in decreasing order. And this process continues. This was one of the green edge which was going across clusters, but the oracle said no, it's not a green edge, and that it gives a cross answer. So we get the correct clustering if the oracle was assumed to be perfect. But as I mentioned, oracle can't be perfect, and let's see what happens to this algorithm when there's an error in the answers given by the oracle. So the same example, it starts very well, everything goes perfectly, but oracle says that these two orange shirt people are the same. And we get an answer from the oracle that they belong to the same cluster, and we end up adding these nodes to the same cluster with a single evidence that they are the same. So clearly this is not the correct approach to follow. Sorry. So how do we approach this problem to nullify the effect of error which is present in the answers of the oracle? So to solve this problem, we propose an error correction layer which can be applied on all the perfect oracle strategies proposed in the literature to handle the noise. And the benefits of a different layer of error correction on top of perfect oracle strategies is that it maintains the performance guarantees of different perfect oracle strategies. It is easily tunable with respect to the performance and accuracy, and it's easily adaptable on all the different strategies. So let's look into this error correction layer, what it consists of, and what are the key ideas behind it. So one of the key ideas behind this layer is that when you get a new node, and you want to figure out whether this node belongs to this cluster or not, you should ask multiple edges instead of a single edge from the oracle. For example, in this case, I ask these three edges. I get two edges as green from the oracle and one as red. There's a majority which says that it's probably a green edge, so this node should belong to the cluster, and I add this node to this cluster. Now, once I've grown a cluster, I should look at all the min cuts of the queried edges of that cluster. So the reason we should look at min cut is that suppose the oracle gave wrong answers and I tried to merge two different clusters, then all the edges going across that cut should be wrong, because the oracle said that all these are green edges. So we want to strengthen the min cuts of the queried graph. So to strengthen the min cuts of the queried graph, we borrow the notion of expander graphs from the theory community, which is well studied in that community, which says that if you consider any graph, any cut of the graph, there should be a gamma fraction of edges going across the cut. So the confidence of every cut is at least gamma. And they also studied that random d-regular graphs are expanders with high probability. For example, this is a graph which is an expander with gamma 2. Like if you consider any cut, the number of edges divided by the number of nodes is at least 2. So this helps us maintain the strength of every cluster which we are querying. Now let's look at a simple case study how this algorithm performs. So these are the different set of clusters on a Cora dataset, which is a bibliographic dataset. The first image shows the ground truth, where the two nodes belonging to the same cluster are joined by a blue colored edge. So the denser regions are the ones which refer to the same clusters. The second image in the middle is the noisy oracle answers of the queries which are asked by our algorithm. There are many more noisy answers, but these are the answers returned as same cluster edges which were asked by our algorithm. And as you can see, the red marked portions are quite messy in this. But the third image shows the returned clusters by our algorithm after asking the answers of the second image. So what does our algorithm do that it clears out such a lot of mess? So our algorithm asks random pair queries with a cluster C when it tries to add a node to a particular cluster. And if it gets a logarithmic number of green edges with respect to that cluster, the node is added to that cluster. But as you can see, the cluster is going to grow as you add nodes. So the size mod C would grow. So you need a larger number of green answers to keep the node in that cluster. So as the cluster grows, some nodes might become low confidence nodes. So after the cluster C grows, you need to boost the confidence of those clusters. How can you boost the confidence of those clusters? So for boosting the confidence, we propose a boost F-score method, which consists of two phases, merge phase and the split phase. Merge phase tries to boost the recall, and split phase tries to boost the precision of the clusters. So how does merge phase work? Merge phase iterates over different clusters in decreasing order of benefit. The benefit can be computed using the probabilities which were given to us initially. And using those benefit values, we query the pairs of clusters to figure out whether they should be merged. For example, if the oracle said these were the two different clusters initially, and we feel that these should be probably merged based on the probability values, we'll ask more queries. The dotted lines are the ones which we ask, and now green has got a majority over the red edges, and we merge these two clusters. Similarly, for the split phase, what it does is that it iterates over the different clusters and figures out which nodes are the low confidence nodes. For example, this red shirt guy has a low confidence because it has just 2 edges. Rest all the nodes have like 3 edges at least. So it will ask more queries for that low confidence node and figure out whether this node should be present in this cluster or not. And it queries more edges, and the green could never get a majority, the red got a majority, and this node is pulled out of that cluster. In this way, it tries to boost the precision of all the nodes and maintain the expander properties of the different clusters. Let's look at the main approximation result. The query complexity of our approach is the query complexity of perfect oracle strategy times log n. So it adds a redundancy of log n because it asks logarithmic number of queries. But in practice, if you look at the plot, as we change the error from 0 to 0.1, our algorithm performs as good as the ideal curve. But even if the error goes up to 0.2, the query complexity does not change by a lot. So our algorithms are much more stable with respect to the error rate. Now we discussed what is present in the error correction layer. Now you could choose to apply that error correction layer on top of perfect oracle strategies eagerly. Like I wanted, for every query given by the perfect oracle strategy, you would call our error correction layer to go to the oracle. So if you apply that eager strategy, you will have a high precision in the clustering returned, but the progressive recall would be low because you will be asking logarithmic number of queries even when it is not needed. You could be very lazy that you will always consider the perfect oracle strategy and not the error correction layer initially, and towards the end you are like, I'll call boost F-score to boost the precision and recall and then return the clustering. The lazy approach will give a higher progressive F-score because initially it boosts the recall quite a lot, but then it plateaus out at a lower precision. And then it gets a lower final F-score. So as you can see, these two techniques have opposing benefits. So we came up with an adaptive strategy which tries to do the best of the both worlds, and it changes the redundancy level depending upon the answers. If the answer matches is same as the matching probabilities, it does not call the expander error correction layer. But if they don't agree with each other, it calls the expander layer. So it tunes accordingly. It gives a high progressive F-score with a low loss in precision, and the loss in precision is later on covered by the boost F-score method called in the end. So if we look at the different scenarios, this table shows that what are the different scenarios that a data set could have. The L and H says that the error rate is low or high. C and U say that the probabilities which are given in the input graph are correlated with the oracle answers or not. As you can see, in all except the LU, adaptive is dominating over eager and lazy. But LU is not a very realistic scenario, but because what it says is that the crowd is perfect, but the edge probabilities are completely noisy. which is not a very realistic situation. Now let's look at some of the experiment results. These are the two different data sets. Cora is a text data set, bibliographic data set. Captures is an image data set. And as you can see, the adaptive pipeline is very robust and much better than eager and lazy and votes and dense, which are the other techniques for error in the literature. Also, you could see in the Cora data set that eager gets a poor progressive F-score, but it gets a higher final F-score. On the other hand, the lazy has a very high progressive F-score, but it plateaus out at a much lower F-score, but around 3,500 queries, the boost F-score kicks in, and it tries to boost the F-score again. As compared to the other techniques like Waldo, our algorithms are much more robust, and Waldo is a technique which queries six nodes. So what it does is that it shows 6 nodes to the user and asks them to return the clustering of those 6 nodes. So in some sense, they get 6 choose 2 answers from a single query. And our algorithm, as you can see, is much better than that too. I would like to summarize the key contributions of our work. We proposed a robust expander toolkit, which is easily tunable, provides high precision at a low loss of, at a low level of redundancy of logarithmic queries. And we proposed 3 different pipelines on how to use this robust expander toolkit, and experiments show that this technique dominates over the others. Thank you. So the probabilities of the pairwise probabilities which we calculate for each node is based on the attributes. So like the Jacquard similarity over different attributes. So we assume that we're given the probability values, like which could be like the Jacquard similarity over different attributes, and you take a weighted Jacquard over different attributes.
Hi, I have 2 questions. The first one is how tolerant is your algorithm in terms of the noise? In other words, how noisy the answers are, then you will basically do not generate good results.
So experimentally, we figured out that up to like 25 to 30% of error, our results are much, like they reach a very high F-score of like 90% or 95%. Mm-hmm. More than 30% error, it starts to get more noisy.
Mm-hmm. Thank you. And the second question is, can you remind me what is the size of your 2 experimental data set? I remember you need about like thousands of training questions.
Yeah, so that's a good question. So the Cora data set has around 1,800 records, and Captures is a little smaller data set which has like 400 to 500. But in the paper, we have an experiment on DBLP, which is of millions. But the results are still like a large number. So we are trying to make the technique scalable in the future work.
Okay,
That's
thank
an
you.
interesting problem. Thank you.
So is your algorithm available for the other research community? Yeah. Okay, but it's in GitHub or is it on your webpage?
We're participating in the reproducibility soon, and we'll make it public.
Okay, thank you. All right, thanks again. Let's go on to the next talk. So the next presentation is by Siddharth Mujal from University of Wisconsin-Madison, and he has many co-authors also from industry, and he's one of the first papers, I think, investigating deep learning for entity matching.